Our next speaker is Carl Pomerance. There. Let's see if this works. Yes.
Thank you. And also thank Mel and Kevin for organizing this conference and many other conferences.
It's displaying the camera. Now it's working.
Paul Erdős used to joke that people would ask him, what if somebody solved all of your problems? Would you have enough money to pay off? Because he had bounties for his problem. And he would say, well, the chance of that happening is less than the chance of everybody going to the bank and withdrawing all their money all at once and the financial system collapsing. Well, with AI now, we may have both of those things. All of Erdős problems solved and the financial system collapsing. So, in fact, over the last few weeks, there were some sensational announcements of progress on Erdős problems in combinatorial number theory. And particularly, there was the unit distance conjecture that was disproved by an AI. This paper that's displayed here is the people listed sort of verified that the AI proof was correct and gave some thoughts about it. The unit distance conjecture is about if you have points in the plane, endpoints, how many pairs can be at distance 1 from each other. Then there was also the real version of the sum product problem. So for this, you probably know it, but I'll just mention what it is. If you look at the integers from 1 to n, and look at the addition table, there are fewer than 2n numbers in, not much more than n itself. But if you look at the multiplication table, there are close to n squared numbers in it. On the other hand, if you look instead of 1 to n, you took the first n powers of 2, then the multiplication table is sparse, and the addition table is has a half n squared numbers in it. So on one hand, one is big and the other is small, and then on the other hand, it's reversed. And the Erdős and Semmelrogge conjectured that if you add together the number of sums and the number of products of an n-element set, it should be big. It should be close to n squared. And in fact, their conjecture was generalized. Who says it has to be integers? It could be real numbers. And in this context, it was disproved. Now, it's not an AI proof, but I think AI was involved somewhat in it. This talk is on more mundane stuff, and I'm going to talk about two unrelated topics, both of them, broadly speaking, in combinatorial number theory. The first one is on subgroups of the multiplicative group mod n. So this begins with Erdős, as a lot of things do in this subject. I like this drawing of Erdős. It was in a children's book about the man who loved mathematics. In writing the slide, I realized all of a sudden it's now 30 years since Erdős died. Yeah. It doesn't seem like that, especially with all the interest in Erdős problems these days. They live on. Well, I guess they're getting killed. So 40 years ago, Erdős and I published a paper about this subset of the multiplicative group mod n. It's a subgroup. It's the basis A mod n, where a to the n minus 1 is 1 mod n. Now, why is this an interesting set? Well, as I just mentioned, it's a subgroup. Notice that if n is prime, it's the full subgroup by Fermat's little theorem. And if n is composite, well, it's the basis for which n is a pseudoprime. That's the definition of a pseudoprime. So we proved that if you looked at the cardinality of this set, that it was generally pretty small when n is composite. In particular, we proved this theorem, that if u is a positive real variable, and you look at the set of composite numbers n with f of n less than or equal to log of n to the u, well, they're all composite, I suppose, because if n is prime, then fn is big, then this set has a density, and it's a function of u that's continuous, strictly increasing, and tends to 1 as u tends to infinity. There's a distribution function. Also, we showed on average that the cardinality of this subgroup of the multiplicative group is small, but not too small. In fact, we conjecture the upper bound there. By the way, this logs of 3 of x, logs of 2 of x, these are iterated logarithms, as is common in Erdős land. And he has a result with maybe a 6-fold iterated logarithm in it. So anyway, the upper bound can be proved if you assume some natural conjectures about the largest prime factor of the shifted prime. But short of that, we just have a power of x. So that exponent 15/23 is about 0.65, and there have been various results about the largest prime factor of the shifted prime, or the shifted primes that are smooth. And the latest result is due to Lichtman, who's here at this conference. I'm not sure are you here in the room, Jared? Maybe not. He gave his talk yesterday. And his result is that you can have an exponent that's about 71.71. Okay, so as I mentioned, we conjecture that the upper bound is tight and up to the little o of 1 exponent. And I'm going to let L of x be that expression with the iterated logs. You'll notice that when n is prime, f of n is n minus 1. It's the full subgroup, as I mentioned. But there are other n's other than primes where you get the full subgroup. In particular, Carmichael numbers. That's the definition of a Carmichael number, that you get the full subgroup. Every coprime residue mod n, A, satisfies a to the n minus 1 is 1 mod n. And so when n is a Carmichael number, f of n is equal to phi of n. Now, after work from Erdős and then subsequent work of mine, we proved the upper bound, that same upper bound, x over L of x to the exponent of 1 plus little o of 1, for Carmichael numbers. And we also showed that this is heuristically best possible. In fact, the first paper of Erdős that touched on this subject was from 1935, published when he was 22 years old. So the Carmichael numbers alone would give most of the story in our theorem, which has relevance to what comes next. Okay, so why am I telling you so much about this result from 1986? Well, just last November, Henrik Lenstra wrote to me in an email about this count, number of A mod n, such that A to the n is congruent to 1 mod n. This is almost the same as my function capital F of n. There the exponent was n minus 1. Here the exponent is n. But nevertheless, it's still a subgroup of the multiplicative group mod n. This is, so in his email, let me just quote to you what he writes. He has a distinctive way of talking, a funny way of talking. So that you may judge for yourself. If I had a Dutch accent, I would do. So that you may judge for yourself how interesting or non-interesting the function psi is, let me tell you the ring theoretic result in which I encountered it. It comes from work that I've been doing together with Ike Das, a recent Leiden PhD now in Luxembourg, and Lars Post, a Leiden bachelor student, on the subject of a classical theorem of Jacobson from 1945. This theorem asserts that if n is a positive integer and R is a ring with the property that all x's in R satisfy x to the n plus 1 equals x, then R is commutative. For n equal 1, this is a very classical result. Using x squared equals x for x equal to minus 1, a, b, and a plus b, one deduces readily that ab equals ba. So 4 x's are sufficient. And I was quite surprised when I learned that still for n equal 1, 2 x's suffice, namely x equals a and x equals ab minus ba. That is a charming and not entirely trivial exercise. In fact, I tried this charming exercise and I didn't succeed in proving it. Whether a single x does it, we do not know. How is this for general n? One of our results is the following upper bound for the number of cleverly chosen x's that suffice. It's phi n plus this new function psi n plus twice the ceiling of log of tau of n. Tau of n is the number of divisors of n, divided by log 2, plus some extra term, which he describes explicitly and is an integer and is either 0, 1, 2, or 3. So the issue is to understand the function psi of n, which Lenstra wrote to me, he calls the new kid on the block. So instead of just looking at psi of n, as Lenstra suggested, I thought, why not generalize to, that would take his function and my function with Erdős and generalize them both. So you fix some integer j, positive or negative or 0, and you look at this subset of the multiplicative group mod n, where a to the n minus j is 1 mod n. So my f of n is now f sub 1 of n, and Lenstra's psi of n is f sub 0 of n. It was not completely straightforward, but I did manage to show that the results for f sub 1 of n do indeed generalize to each f sub j of n. Remember, there was a special subset when, a special case when n is 1, namely the primes, when you get the full subgroup. And you can ask, and that can throw off counts, but there are a lot of primes. So how do you generalize that? And so when j is 0 or negative, there's no analog. You don't have to worry about that. When j is positive, the to say n is composite, that generalizes to when j is a divisor of n, then n over j is composite. So when j is 1, that's just saying that n is composite. So it turns out that in Leinster's case, j equals 0 was the most difficult to generalize. So the proofs didn't exactly work, and some other tricks were done. So let's let lambda of n be Carmichael's lambda function. It's interesting that we call it that because maybe that's the notation that Carmichael used, but it was already appeared a century earlier in Gauss's Disquisitiones. He didn't call it lambda of n. So basically, what is it? It's the exponent of the multiplicative group mod n. It's the least positive integer such that every coprime residue A mod n has order dividing at lambda of n. So we've seen that Carmichael numbers, they're composites n with lambda of n divided by dividing n minus 1. They play a special role with f sub 1 of n. For j equals 0, the special role is played by those n with lambda of n dividing n. Lambda of n dividing n, that's a strange property. You think of some numbers with that property other than n equal 1? Well, here are some. Take any number that's 3 smooth and even. So 2 to the a times 3 to the b with a positive. The Euler phi function of that is either 1/2 of that or 1/3 of that. So phi of n divides n. And so lambda of n would divide n. This lambda of n is divisor of phi of n. Here's another example, 20. Lambda of 20 is 4, and 4 divides 20. So maybe it's not so unusual. Anyway, if that happens, then Luca and I proved that that number n is in the range of every iterate of lambda. And in fact, 20 is in the range of every iterate of lambda. Look at the jth iterate of lambda. Well, what is lambda of a power of 5? It's just the next smaller power of 5 times 4. And if you take lambda of that, 4 doesn't matter because you already pick up the 4 from the 5. So what we get is that 20 is in the range of every iterate of lambda. Here's an unsolved problem for the problem session. Is 10 in the range of every iterate of lambda? We don't know. Okay, let's let lambda, capital lambda, be the von Mangold function, and define this additive function g of n, which is the sum over d dividing n of lambda d over phi of d. So I proved that for every integer j, there's a set S sub j of integers of asymptotic density 1, such that f sub j of n is pretty much determined by this function g. This log of n to the power g of n minus j plus little o of 1. And this holds for almost all n's as n tends to infinity. So Erdős and I proved this for j equals 1, and that's how we got that theorem about log of n to the u that I mentioned earlier. So the Erdős-Vintner theorem allows you to make that jump. Another interesting problem is to fix A, not look at the subgroup mod N, but to look at this in maybe the N aspect, as it said. So you fix A, like A equal 2, and ask for the N's where 2 to the N minus 1 is 1 mod N. So in particular, that's just the case of pseudoprimes, base 2. So the conjecture is, again, that we get x over L of x. The best that we're able to do is x over the square root of L of x. In fact, we can prove this uniformly for all a's up to x, as x goes to infinity, which was done in a recent paper I have with Shuguang Li. Another question you can ask, how many different subgroups are there of the form that I've been considering in this talk? It turns out that you get one of these for every divisor of the Carmichael function, and that's how many there are. If you want to look at statistics of the number of divisors of the Carmichael function, well, Florian Luca and I have a paper about this. And the general question of how many subgroups in total are there of the multiplicative group mod N? Well, there are two versions of that question. One is you can ask how many subsets are subgroups, and then how many subgroups are there up to isomorphism. And both of these questions have recently been addressed in papers of Greg Martin and Lee Troop. Okay, so now I'd like to begin my second topic, which is not related, as far as I know, to the first topic. So here's a simple question. Given two intervals I, j of n consecutive integers, is there always a one-to-one correspondence from I to j? This is a question to make sure that you're awake. You'll notice the question doesn't have a question mark after it. That's because I didn't finish. Okay, with corresponding numbers relatively prime. So there has to be a extra condition to make it an interesting question. So we're asking for a matching in the coprime graph. And the quick answer to this simple question is no. So for example, consider the singleton set 4. That's an interval of one consecutive integer. And the singleton set 6. That's a singleton set of one consecutive integer. There's no coprime matching from 4 to 6 because they're not coprime. Okay, say the sets have to have cardinality bigger than 1. Well, here's another counterexample. 3, 4, and 5, 6. Why is that a counterexample? Because 6 is not coprime to 3 and it's not coprime to 4, so you can't match 6 with anything. Here's another example, 4, 5, 6, 12, 13, 14. The trouble here is that both sets have a majority of evens, and you can't match an even to an even. As we've already seen with 4 and 6. So it looks like we should leave this. Too many counterexamples. But I even have another even more complicated counterexample, 10, 11, 12, 13, 15, 16, 17, 18. You can read there what the problem is. Okay. So around 1960, D.J. Newman conjectured that there would be a coprime matching if one of the intervals is 1 to n. In a lecture in 1962 at the University of Reading, Erdős offered £5 for a proof of Newman's conjecture in the case where the second interval was n plus 1 to 2n. And two professors there, Dakin and Baines, proved this weaker conjecture. And Mike Baines, I wrote to him, he told me that they collected 2.5 pounds each. British was good for his word. In 1971, Vaschek-Schwafel proved the full Newman conjecture, but only for n up to 1,000. It looks like Newman's conjecture is correct, but maybe can it be proved? Here is Newman and Schwafel. So I write here, in 1979, I attended a conference in Carbondale, Illinois. Mel perks up. You organized that conference too. You're an old hand at organizing conferences. We were both fairly alive. So at that conference, John Selfridge told me about the Newman conjecture, and he told me why he thought it was true and why he thought it might be provable, and suggested that we team up. And so I followed his plan, and we proved it in 1980. So fast forward 41 years to 2021. Tom Bowman and Fei Peng, a graduate student of Bowman's, posted a paper to arXiv, and they proved the following. So remember, if one of the intervals is 1 to n, it can be done. That's Newman's conjecture. And if they're both not that interval, there can be problems. So the question is to get it in a situation where there wouldn't be problems. So first of all, they said, but the n has to be even. Why does n have to be even? That guarantees that both sets have an equal number of odds and evens. And you can't have a majority even case like we saw was possible. And secondly, we're going to put both intervals inside of a big set, 1 up to capital N. And we're going to say that they comprise at least some substance of that big set. So the more than e to the c square of log n. And if so, there's a coprime matching. Then they used this result to prove a weak form of another conjecture in combinatorial number theory known as the lonely runner conjecture, which I'll tell you about in a minute. So I was intrigued by this post to arXiv, and this I'd worked on coprime matchings, and because I had worked on the lonely runner conjecture. So I studied that paper and I found a way to improve it, and instead of forcing little n to be bigger than e to the c log n squared, I just got it bigger than constant times the square of log n. Here's Bowman and Peng with a typo in Bowman's name. So the lonely runner conjecture. Suppose V1 through Vk are distinct positive integers. It says that there's some real number t such that the fractional parts V1t up to Vkt are all bounded away from 0 and 1 by 1 over k plus 1. So one thinks of this as k runners on a circular track of length 1, with v sub I being their velocities. And the special time here makes a k plus first runner with speed 0, who's always at 0, is lonely because none of the other runners are within 1 over k plus 1. So this was proved by k equal 4 by Tom Cusick and myself for k equal 5 by Bowman, Holtzman, and Kleitman, and for k equals 6 by Barchas and Serra. Terry Tao showed that in the general case, when all the velocities are not too much bigger than the number of velocities, less than or equal to 1.2 times k, then it's true. And so the new result of Bowman and Peng, the application that they gave of their coprime matching, was to replace 1.2 with 2 minus epsilon. And my improvement of the Bowman-Peng result gave just a smaller epsilon, so it wasn't a very exciting improvement. Here's a picture that I love of Erdős and Tao. Again, just a baby, as you were saying. So instead of matching 1 to n to another interval of n numbers, the other interval could itself be 1 to n. And in fact, that's easy to arrange. You can just take the cyclic permutation. 1 goes to 2, 2 goes to 3, and so on, n goes to 1. And that's a coprime permutation. So it always exists, but maybe it would be interesting to count how many there are. So let C of n be the number of coprime permutations of 1 up to n. So for example, there are 4 of them if you have 1 up to 4. It's not hard to count. You just have to be aware of evens and odds. So the numbers 2 and 4 can be mapped to 1 and 3 in any order. And the numbers 1 and 3 can be mapped to 2 and 4 in any order. So you have 4 choices. And those are your 4 coprime permutations. So I asked a colleague of mine at Dartmouth, Sergi Elizalde, if he knew anything about this problem. So he did something that I'm slow on the uptake. I guess it's common for the younger generation. Just put it into OEIS and see what you see. And so he computed the first few terms, put it in OEIS, and discovered exactly that this had been studied by a Canadian combinatorialist, David Jackson, and he computed it up to 24. Furthermore, he had an interesting take on what this count is. You consider the n by n matrix, where the ij entry is 1, if I and j are coprime, and it's 0 otherwise. So it's a 0, 1 matrix. It's the adjacency matrix for the coprime graph on the integers from 1 to n. And then the number of coprime permutations is the permanent of this matrix. I had never heard before of any application of the permanent. It was always given as a computational problem. It's hard to compute it, but I didn't know it had any use, but here's a use. But because it's hard to compute, that means that I couldn't go much beyond 24. I think I got up to 50 using Mathematica, but that was sort of painful. Then I was able to prove, using some of the techniques from my old paper with Selfridge, that C of n grows, well, the numerator n factorial is bigger than any fixed power of n, so that's the key takeaway, but the denominator is some power of n. So Nathan McNew, who will be speaking in this conference on Thursday, identified a constant c and conjectured that it should be n factorial over c to the n, up to a small factor. And then Sa and Sani, who were grad students at MIT at the time, proved it. So here's Sa and Sani, and here's McNew. So Nathan and I just wrote a paper that was published within the past week in Mathematica about matchable numbers. So this also deals with the coprime graph. So maybe it's hard to read that abstract, so let me just tell you what it is. So tau of n is the number of divisors of n. And we can look at the set of divisors of n. That set is as cardinality tau of n. And then we can take the initial interval 1, 2 up to tau of n and ask, between those two sets, is there a coprime matching? And if there is, we say n is matchable. This was introduced by Reckermann on Math Overflow in 2022. And he asked if more numbers are matchable than not. So here's an example of a matchable number, 6. 6 has 4 divisors, 1, 2, 3, and 6. So you can see the matching here, where the divisors of 6, 1, 2, 3, and 6 are the left sides of the double arrows. And the numbers 1, 2, 3, 4 are the right sides of the double arrows. And each double arrow is a coprime matching. Now, the number 8 is not matchable. In fact, it's the smallest non-matchable number. The divisors are 1, 2, 4, and 8. And you'll notice that the set 1, 2, 4, and 8 contains 3 even numbers. But 1, 2, 3, 4 contains only 2 odd numbers. So in a matching between them, you're going to have to send an even to an even. And that's not allowed for a coprime matching. In fact, all the multiples of 4, starting at 8, are not matchable by the same argument. And so we've instantly proved that density 1/4 of all numbers are not matchable. But it seems like maybe the matchable numbers should be in the majority. And Reckermann asked that question, are there more numbers matchable than not? Well, here are some more numbers that are not matchable. Just like multiples of 4 are not matchable. If you take a multiple of 27, where the 27m, where m is composite, then it's not matchable. So 1/27th of all numbers are of the form 27m with m composite. And so what we get is that we're carving away these non-matchable numbers, and what we're left with is a set of size 1 minus 1/4 times 1 minus 1/27th. And that generalizes to other primes, and you can carve away all those primes, and you're still left with quite a lot, about 0.722. 72% of all numbers are not ruled out by this sort of trivial argument. And our theorem is that that's the answer. That's the asymptotic density of the matchable numbers. On the way to proving this, we showed that every square free number is matchable, and that too would give a majority. But it's not as big as 72%. Let's say a number is an M number if it is not divisible by any p to the p. That's sort of what I just computed the density of. So what we do is we show that for a possible exceptional set of density 0, every M number is matchable. And that the set of non-M numbers that are matchable has asymptotic density 0. That was relatively easy. The first one was the hard one. And we conjecture that that first set is empty, that every M number is matchable. So let's say n is strongly matchable if there's a coprime matching between the divisors of n and every coprime arithmetic progression of length tau of n. So, for example, although the number 4 is matchable, it is not strongly matchable. 4 has just the 3 divisors, 1, 2, and 4, and you can't coprimely match that to 2, 3, and 4. It's easy to prove that every strongly matchable number is an M number, and we conjecture the converse. But we were only able to prove that a positive proportion of the M numbers are strongly matchable. So Scott Commoners was interested, and he computed this and sent me the graph, so I'm running it on the talk. The blue line is shows the density of matchable numbers, and the orange line gives the density of the M numbers. So we proved that in the limit, the blue line is going to hit, not hit, but be asymptotic to the orange line. Anyway, that's the nice picture. So in McNew's talk on Thursday, he's also going to talk about matchable numbers and give more details than I've given. Okay, so let me close this talk with the opposite of the coprime graph, and that's the divisor graph. So here we connect two integers that are not equal if one is a divisor of the other. So for example, Erdős asked this question. What's the longest chain in the divisor graph on the numbers 1 up to n? So you want to take a sequence A1 through AK, all less than or equal to n, where either A1 divides A2 or vice versa, A2 divides A3 or vice versa, and so on. Erdős conjectured that length of this is little o of n. And I proved that, and other people who've worked on this, Andy Pollington, Sayas, Tenenbaum, and McNew. You can also ask how many permutations are there with the property that J gets sent to either a multiple of itself or a divisor of itself. So I've written about this, and so has McNew. Now, let's let f of n be the least number such that in every interval from n plus 1 to n plus f of n, you can find distinct integers, a1 through an, with I dividing a sub I. So for each I up to n, there's a distinct multiple of I in the second interval. And you'd like that second interval, starting at n plus 1, to be as short as possible. And then we maximize that over m, and we get number f of n that's true for every m. So 46 years ago, I proved with Erdős that this f of n is slightly bigger than n, like n times square root of log n, and smaller than n to the 3 halves. Just earlier this year, Van Doorn improved the lower bound to n log n over log n. And then just essentially now, Commoners has removed the log n. And even more recently than now, Noah Leibowitz-Lockhart, who's here at this conference, here in this room, claims to even do better. Well, hopefully he's right. Anyway, thank you for your attention.
Questions for Carl? Yeah. Oh, sorry, but you have to repeat the question in the microphone.
Okay, I'll do that.
So one question would be, is there some graph theoretic result about matching which are used in these theorems? So you form a graph like pairs.
Well, for all of these matching problems, a huge tool is the Koenig-Hall marriage lemma in graph theory.
And my second question, because it's an average, is it known about the density of the pairs of sets, n elements of the capital N, then there is a matching, like how many, like a random set? Or
I don't know. That sounds like a nice question. By the way, all the graph theorists call it Hall's theorem. Erdős called it Koenig-Hall, and Koenig didn't exactly prove the same thing, but it was similar. So interesting.
Apparently £5 in 1962, was it? It's roughly £140.
No.
Yeah. Yes.
Oh my God, I'm wondering when it's sending it to the city.
Everybody.
Other questions? Monetary or otherwise? No. Okay, let's make Carl again. Carl. So.
What?
You at the very end, you mentioned the value of factorials. Yeah, so if we actually prove that, or if we use that, Bishop, yeah. This goes out. Yeah.